Welcome to this week's first lecture in EE404. In the last lecture, we have started investigating the phase-plane trajectories of nonlinear systems. So far, we only made a local analysis based on linearization around equilibrium points. And in this lecture, we're going to see that for some specific nonlinear systems, we can actually extract or obtain the expressions for the global phase-plane trajectories of nonlinear systems. But as I just told you, it is only for a very, very specific nonlinear systems that we can do this for, which would result in separable differential equations. And for more complicated systems, unfortunately, in order to be able to obtain global phase-plane trajectories, we need to resort to a computer. So here we are going to see the topic is the drawing global phase portraits or phase-plane trajectories of nonlinear systems. In this case, we are actually going to see two different methods that we can apply here. The first method, I will illustrate it on an example. Both methods I will illustrate on examples. So here we are given a nonlinear system, x1 dot is equal to x2 and x2 dot is equal to, I have here, this is x2 square, and I have x1 here. All right? So this is our nonlinear system, and you see that the nonlinearity is in the first equation. The second equation is linear. And what we have to do is to draw the trajectory of the system starting at, so we are given an initial condition, x0, and that is equal to -1 and 1 here. All right? So we are given the initial conditions for both of the state variables. So this is my x01, and this is x02. In this case, you see that we don't want a phase portrait. A phase portrait is the drawing of multiple trajectories at the same time on the same figure. And here we are asking for a single trajectory, and I will apply the methodology. So in order to be able to obtain a phase portrait, you have to apply the same methodology over and over for different initial conditions. Only in that case will you be able to obtain a phase portrait. So here the first thing that we are going to do is that we are going to eliminate time. Remember, a phase portrait is nothing but the drawing of the state variables with respect to each other. If I can find x2 in terms of x1, that gives me a trajectory, and in order to be able to therefore obtain a phase-plane trajectory, I need to cancel the variable time from those equations. The canceling time is actually quite easy here. The first thing that I do is to write these derivatives as follows. dx1 over dx2 is, dx1 over dt is equal to x2 square, and dx2 over dt is equal to x1. And here, from these two equations, I need to cancel time. These equations depend on three quantities, x1, x2, and time. And a phase-plane trajectory is nothing but a function of x1 and x2 only. Okay? Or if we can write x2 in terms of x1, or if we can write x1 in terms of x2, then we would get the phase-plane trajectory. So we don't want the result to depend on time. That is why I want to cancel time from these equations. So here is what we're going to do. These are the derivatives with respect to time. I'm going to take the ratio of the left-hand sides and the right-hand sides here. So I would have dx1 over dt divided by dx2 over dt. That is equal to x2 square over x1. All right? Now actually I'm going to do something magical. I will cancel these dt's from here. Okay? So if I cancel these dt's from there, I would get the rate of change of x1 with respect to x2. All right? So you see it's really very, very easy. The x1 over the x2 is equal to x2 squared divided by x1. Okay? So we see that we get a differential equation in this case, which is given in terms of only the desired variables x1 and x2. So the only thing that I need to do afterwards is that to solve this differential equation to obtain either x2 in terms of x1 or x1 in terms of x2. Okay? So this type of differential equations in mathematics are called separable differential equations, and this is a limitation of this method. If the differential equation that we obtain afterwards is not separable, then we will not be able to use this methodology. Okay? So that is a limitation actually of this method 1. But these type of differential equations are called separable because I can collect all of the x1 terms and I can collect all of the x2 terms on different sides of this differential equation. And here is what I'm going to do. I will take this x1 to the other side and I will write x1 times dx1. That is equal to, and I will collect all of the terms with respect to x2 to the other side. x2 squared dx2. Okay? Then I will integrate both sides to get rid of these dx1s, dx2s. Okay? Integrate the left-hand side, then I'm going to get, I have x1 squared over 2. I'm integrating with respect to x1. The integration of x1 with respect to x1 is x1 squared over 2. And I have a constant c1 here. Okay? We always have a constant. So when I take, so that this is a constant with respect to x1, so that when I take the derivative of this quantity with respect to x1, I would get just x1. This c is going to give me 0 there. That is equal to, I will take the integral of this thing with respect to x2 now, x2 cubed over 3 plus c2 here. All right? So now what I'm going to do is actually, I will take both of these constants on the same side, and I will write this equation as x1 squared over 2, and I have here x1 cubed over 3 plus c2 minus c1, but that is just another constant for me, okay, which I call as c. So in general, after I collect these terms on both sides and after the integration, I will not actually write two different constants here. Okay? I will just write a single constant, and therefore I will not write the constant with respect to the first integration, and I will and for both of them I will just write c here. Okay? C is a constant now. Now what I have to do is to find that constant. This is the equation of our trajectory, and I need to find this C based on the initial conditions of the differential equation. So here we are given the initial conditions as x1 of x1 0 is given as -1, and I write this as x01, and this is x02. It is equal to 1. So I made another mistake here. So I have x2 cubed here. Now instead of x1, I substitute -1, which gives me 1 over 2. And instead of x2, I substitute x02, which is giving me 1 over 3 plus c. Okay? And then this thing is going to give me c equals to 1 over 2 minus 1 over 3, which is equal to 1 over 6. All right? So now I can actually go back to this equation, and I would obtain the exact expression of my trajectory without any unknown constants. Okay? Plus 1 over 6. And now, in order to be able to draw this trajectory, I will leave x2 alone on one side. So let us write x2 cube over 3 is equal to x1 square over 2 plus 1 over 6. Now let me multiply both sides of this equation with the constant 6. Then that is going to give me 2x2 cube is equal to 3x1. Another mistake here. This is going to be minus 1. So I have 3x1 squared minus 1. Okay? And let us try to extract x2 from here. x2 cube is equal to 3x1 squared minus 1 over 2. And then x2 is equal to, it is the cubic root. I have x1 squared minus 2 divided by 2, given like that. So this is the expression of my trajectory. Now I need to draw this onto the state space in order to be able to obtain the phase plane trajectory. So I will go step by step. Drawing this trajectory from start immediately might not be easy. That is why I'm first going to start by drawing what x1 square is. x1 square looks like this. Okay? That is x2 is equal to x1 square. I will obtain 3x1 squared. That is going to be looking like something like this. So 3 times this parabola here. It has to be symmetric. So this is 3x1 squared. And then I will subtract minus 1. I will subtract 1 from 3x1 squared. So I will take this curve here, and I will pass it from minus 1, and I will make it parallel to 3x1 squared. So it's going to be looking like this. Okay? This is 3x1 squared minus 1. I can also write it. And then I will divide everything by 2. Maybe I should use just another color here. So this is the point minus 1 over 2. Then I will divide everything by 2. But before that, let me find these zero crossing points here. So this is 3x1 squared minus 1. This is equal to 0 at 1 over square root 3 and at minus 1 over square root 3. Okay? When I divide this curve when I divide this quantity by 2, these zero crossings will not change. Okay? I will just divide the non-zero parts by 2, and the result is going to pass through here, and it's going to pass through here, and it's going to be half of these parts. All right? So I will have a curve in that case like this, and this is 3x1 squared minus 1 over 2. Now the only thing that I'm going to do afterwards is that I need to actually take the cubic root of this thing. Okay? When I take the cubic root, I will just have 1 over cubic root of 2 minus, and then the zero crossings will not change. So here I can actually try to draw the resulting figure on another axis here. Okay? So I have x1, x2 here. And what I'm going to do is that the resulting figure is going to pass through the point. Let me try to draw. It's not going to be up to scale with this one. So I will write here 1 over cubic root 2, and it's minus. The curve is going to pass through here, and I have here 1 over, it is the square root 3 point, and I have, this is minus 1 over square root 3 and plus 1 over square root 3. These are not going to change, and everything here will be taken power of 1 over 3. Okay? So I would have this point like this, and we're going to reach here. Now, one detail here is that when x1 goes to infinity here, you see that this 1 is going to be negligible, so the power of x1 is going to be 2 over 3, which is smaller than 1, which means that when this curve passes through this point and when it approaches to the right, then it's going to become a concave curve like this. Okay? This is because of the power here of x1 when x1 goes to infinity. Okay? So this is my trajectory. That is an approximate trajectory for the example. The question now is, we know that each trajectory should have a direction, and here the direction is still missing. How should I choose it? So this is my system here. x1 dot is equal to x2 square, and x2 dot is equal to x1. So we see here that x2 square is always non-negative for this system. x2 square is always non-negative, meaning that x1 dot is always going to be non-negative, meaning that x1 is either going to remain constant or it has to increase. So in this trajectory, therefore, what I need to do is to make sure that on this trajectory, after I select the direction, when I follow that direction, x1 would always increase, and it is going to be just this direction. Okay? So you see that on this curve, then x1 coordinate is always increasing. Okay? Of course, except at x2 equals to 0. And here, but x2 is equal to 0 is just a point there. Okay? So it's not really that important. But do we have the second equality correct as well? The second equality, I really do not have to check it at this point, but let us check also that this holds on our curve. So here this is x2 dot is equal to x1, meaning that if x1 is positive, x2 is going to increase. If x1 is positive, meaning that we are on this part of the x1, x2's plane, or phase plane, x2 is going to increase. We see that when x1 is positive, we are in this part, we see that x2 is always increasing on this curve. Similarly, if x2 is negative, which means that we are in this part of this phase plane, x2 should always decrease, and that is actually what we observe here. On this curve, in this direction, with this direction, x2 is always decreasing. All right? So we can determine the direction using any of the equations there. So this completes this example, and because we are going to do similar things over and over, I will only solve this example now, and I will go into the second method. Okay? Because later, after I finish with both of the methods, later we are going to solve much more examples on this method 1. So method 2 is as follows. This has a specific name in the literature. This is called Isocline method. And it's not only useful for extracting a single trajectory like this, it is useful for extracting multiple or drawing multiple trajectories of the system at the same time. So iso, I think it comes from Latin, and it means the same in English, okay? And cline it means slope, okay? So isocline, if you translate it into English, it becomes the same slope method, okay? We are going to see why this naming is quite accurate for this method. Because this method, while using this method, we always try to obtain actually the curve of the points on which the trajectories of the system have the same slope. Okay? In the Isocline method, we always obtain some curves on which the slope of the trajectories are the same. Okay? Let me try to explain this a little bit. Okay? So suppose that I have a trajectory here. Okay? We have already drawn a trajectory here. And here, what is this slope value at this point on this trajectory? So this is my x1 value there, and this is my x2 value there, and I'm trying to obtain the slope value of this curve at exactly this point, x1, x2. Okay? This is really easy, because you see that we have obtained here x2 with respect to x1. Okay? That is, this is nothing. The slope of this line, the tangent to the curve, is nothing but dx2 over dx1. Okay? So here, at the beginning of the method, we can obtain this dx2 over dx1, and this becomes an expression, of course, in terms of x1 and x2. dx2 over dx1 for the earlier example was x1 over x2 squared. And as a result, in order to be able to calculate the slope of this trajectory at this point here, then I can substitute this x1 value here and this x2 value here, and then that is going to give me the slope of the trajectory there. Okay? So our aim is going to be to obtain actually the points on the trajectories in the state space where this slope is exactly the same on every point on a curve. So here let me try to apply Isocline method to our example. Then you're going to understand it better. x1 dot is equal to x2 squared, and x2 dot is equal to x1. This is our example, and we know that the slope of the trajectories is given by dx2 over dx1. Now we know how to obtain such a quantity. If I divide x1 dot, if I divide x2 dot by x1 dot, I would obtain dx2 over dx1, and that is going to be x1 over x2 squared. All right? Now what I'm going to do is that I'm going to equate this to a constant alpha. Then what we are going to do is that we are going to give some specific values to alpha and try to draw the curves that would result from this equation. Okay? What type of curve does this result in? It gives me a curve, x1 is equal to alpha x2 squared. Okay? Of course, with different slopes, if I choose alpha 1, this gives me x1 is equal to x2 squared. I have to draw that one. And if it alpha equals to minus 1, this gives me x1 is equal to minus x2 squared, etc. All right? So let me draw another x1, x2 plane to draw the trajectories. In this case, you see that I'm not given any initial condition, because actually we will be able to draw multiple trajectories at the same time using the Isocline method. So I have x1, x2 here, and let me take alpha equals to 1. When alpha is equal to 1, that means that the slope of the trajectory on each point on the curve x1 is equal to x2 square will be 1. Okay? So I have substituted alpha equals to 1, then that gives me the equation x1 is equal to x2 square. Let us try to draw that curve. x1 is equal to x2 square. So this is what x2 equals to x1 square would look like. Okay? Here I need to draw x1 equals to x2 square. So it is going to be a turned parabola. All right? So I would have a parabola given like this. This is the curve of the points on which the slope of the trajectories are all 1. Okay? So if a trajectory passes this curve, if a trajectory happens to be exactly on this curve, the slope of the trajectory is going to be equal to 1. Okay? So what does that mean? So if a trajectory passes through this point, its slope is just going to be equal to 1. So the slope is going to be just like y is equal to x line here. Similarly, from this point, I have the same thing. And here, I have a similar thing. And here, I have a similar thing. If a trajectory passes on this if a trajectory happens to be exactly on this line, the slope of the trajectory should be just 1. And I can actually add these lines here as well. Okay? So slope 1, and I would have slope 1. Okay? Now let me try another alpha. Alpha equals to 1 over 2. In that case, the curve on which this slope is achieved is x1 is equal to 1 over 2 x2 squared. Okay? So you see that this is another parabola, and in this case, this parabola is going to be divided by 2. When I look at it like this, it's going to look like a parabola, and I will divide it by 2. All right? So I would have a parabola like this. And we see that the slope of the points on that curve should be 1 over 2. A 1 over 2 slope, this is slope 1, this is slope 1 over 2, and this might be slope higher than 1. Okay? So slope 1 over 2 is going to look like this, a more horizontal line here. Here it's almost parallel. Okay? The slopes, these slopes should always be the same. So my drawing skills is not sufficient here. So the slopes are just 1 over 2 on these lines. And here I would have also a smaller slope. Okay? Let us take alpha equals to 2. Then x1 is equal to 2x2 squared. So this is the curve of the points on which the slope of the trajectories is 2. In this case, this parabola is going to grow faster. All right, so I would have just this. And then the slopes will be, the lines would be more vertical here. Okay? Twice the slope 1. So let me take alpha equals to 0. If alpha equals to 0, then the slope of the trajectories is 0, which means that the trajectories should be locally horizontal. Okay? So what does this equation tell me when alpha is equal to 0? In that case, x1 equals to 0, meaning x2 axis. Okay? So the slope of the trajectories on x2 axis will be just horizontal. Okay? So I will draw things like this. Similarly here as well. Now I can also try the negative slopes. Alpha equals to -1. And in that case, x1 is equal to minus x2 square. It is just a replica of this middle parabola on the other side. So I would just have the parabola like this. And the slope on this parabola is going to be just -1. So I would have -1 slope. In this case, I'm drawing lines like y equals to -x. Okay? And I can also try alpha equals to -2, x1 is equal to -2 x2 square. Then I would draw the innermost parabola, replica of it, and then -2 slope is going to look like this. More vertical lines with negative slope. Okay? And if in order to be complete, if I draw alpha equals to -1/2 line, then that is going to be x1 is equal to -1/2 x2 square, and it is this outermost parabola here. And on that, the slopes would be more horizontal. Okay? So I would draw slopes like this. So in some way, when I try to draw the trajectories, you see that I'm trying to keep the consistency. So you see that there is going to be some trajectory that might be passing from here to here, all right? And the trajectories are going to come here, and then they're going to become more and more horizontal, all right? Now, as a final thing, I will take alpha equals to infinity. So when alpha goes to infinity, what is the equation that I need to take? So here, in this case, it really doesn't make sense to take alpha infinity, because when alpha is in infinity, then I would get an equation x1 is equal to infinity x2 square. It is still meaningful, but in this original equation, maybe it's more meaningful to let alpha go to infinity. If alpha goes to infinity, I see that x2 should be going to 0. Okay? So here, x1 line, so this x1 axis is going to be where alpha goes to infinity. That means that the slopes of the trajectories would be infinity when x2 is equal to 0. Okay? So on x1 axis, the trajectories would be locally vertical. Okay? So I would take vertical trajectories here. Infinite slope. So now we are almost complete here. Now here, what I'm going to do is that I know the directions of the trajectories, but even without knowing the directions, I can actually try to draw a trajectory on this axis here. So here is what I'm going to do. Suppose that I start somewhere at this point. Around this parabola, the slope of the trajectories are going to be -1. And I know that when I reach this parabola, the slope of the trajectories would have to be -2, okay? And then when we go towards inside this parabola, the slopes are going to get more and more vertical, and we're going to be exactly vertical on x1 axis due to this one, x2 equals to 0. And then we see that we start to turn around origin like this, okay? So the slopes are getting more and more horizontal, and while crossing the x2 axis, we become horizontal because of this one. And then actually we're going to have this symmetric part of everything. We are going symmetric counterpart of everything. Why is that? Because of the system equations here, we are going to turn in the other direction, and we are going to become vertical again on the x1 axis, and then things are going to start to get more and more horizontal, and we're going to go like this. Okay? So if I complete this in the other direction, then that is going to be like that. And we know already how to put directions here, and these are going to be looking like this. Okay. So here we see that if x1 is positive, so we see that it really doesn't matter if x2 is positive or negative, okay? But if x1 is positive or negative, we are going to get, if I have this velocity for this x1 and x2, I would have the reverse of that velocity for when I'm exactly on the symmetric counterpart of here. Okay, so at these points I have opposite velocity. I have opposite slope values. Okay, so here I have opposite slope values, etc. Okay, because of this x1 here. All right. Because x2 really doesn't change the slope at all. X2 being positive or negative does not matter. It all becomes the same. So there is no symmetry with respect to x2, but if x1 is positive or negative, if x2 is the same, I have a symmetry of these trajectories around this axis. Okay. So here, this was the single trajectory that we have drawn using the first method, and this is the second method applied onto the same system. Okay? But you see that with the first method we could only draw this single trajectory because that is the only one we could get the equation for. And in this case you can actually draw multiple trajectories at the same time. I know, for example, that there is another trajectory like this for different initial conditions. Okay? Or I might draw some alternative trajectories which would be looking like this. All right? So this isocline method can be used at the same time to draw multiple trajectories on the same figure. Okay? Of course, I need to put here again the directions. So that completes the introduction of the isocline method. Now what I'm going to do is that I'm going to solve one more example on the isocline method. The system that I'm given is the following. x1 dot is equal to x2 and x2 dot is equal to 2 minus x1. And the task is to apply isocline method. Draw the phase plane trajectories using the isocline method. This is almost a linear system. Sometimes we call such a system an affine system because the equations of the system are looking like this. So I have x dot is equal to, there is an A matrix here, 0, 1, and minus 1, 0, x, plus I have here a DC input here, which is 0, 1, and I put here 2. Okay? So this is like a constant input in a linear system. X dot is equal to AX plus BU. So this is a linear system with an input. Okay? In that case, in this form, we call this system just an affine system. Why is that? Because in that case, it is looking like this. X dot is equal to AX plus. This just is a vector, B times a constant. And we see that the right-hand side is linear jointly in X and U, but if I think about it as a function of X only, this term becomes like a constant vector when U is constant. So the right-hand side really looks like AX plus B, where this small b is B times U when U is constant. And the functions looking like AX plus B are not linear functions, but they are of course lines, but they are not called linear in mathematics. They are called affine functions. Okay? So the task is to apply Isocline method on this system. So the first thing that I'm going to do is to write dx2 over dx1. Okay? That is the slope of the trajectories. So I have 2 minus x1 divided by x2 here, and I'm going to equate this to alpha. All right? Let us try to manipulate this equation just a little bit. So I have 2 minus x1 is equal to alpha x2. Let me collect all of the terms related to x1 and x2 on one side. x1 plus alpha x2 is equal to 2. So you might see that, you might realize that this is an equation for a line. And I need to draw such a line for different alpha values. That is what Isocline method tells us. I need to select different alphas, and I need to draw these lines for each of those alpha values. Okay? So that means that it would be nice if I can put this line equation into a standard form. We know that if I have an equation in the following form, x over x0 plus y over y0 equals to 1. Such an equation would show us a line that would pass through the point x0 and that would pass through the point y0. Sorry, this is stupid. So I have xy here that would pass through x0, 0 and pass through the point 0, y0, and that would be this line here. Okay? So this is the parameterization of the line that we can use here. That means that it would be nice if I can put this equation into this form. All right? So we see that the intersection with the x-axis would be at x0, and the intersection with the y-axis of the line would be at y0, and the right-hand side should always be equal to 1. Okay? First, let us make the right-hand side equal to 1 for all alpha cases. Divide both sides by 2. x1 over 2 plus alpha over 2 x2 is equal to 1. But then I'm going to, so this, I don't really want the coefficient of alpha here. I want it to be in this form, x2 divided by the intersection point. So I just write this equation in the following form, x1 over 2 plus x2 over 2 over alpha, okay, that is equal to 1, all right? So this is going to be the standard line equation that we are going to use. Maybe I should get rid of this one as well. It's going to leave lots of marks here, but I need to erase them as well. Yes, this is much better. Okay, now let us start selecting alpha values. Let us say that I select alpha equals to 1. In that case, the equation that we get is that, so here you see that this x1 intersection point, it is never changing. So the lines that I'm going to draw, if I draw my x1, x2 axis like this, then the x1 intersection would always be at 2. Okay, let us say that this is the point 2. So the lines that I'm going to draw are always going to be passing through this point for different alphas. All right? If alpha is equal to 1, then 2 over alpha is equal to 2. This means that this line is going to pass through 2 on the x1 axis, and it's pass through 2 on the x2 axis. So I have this line here. Okay? And on this line, I know that the slope of the trajectories should be just 1. Okay? So I need, the slope of this line is -1, and the slope of the trajectories on this line would be just 1. Okay? Let us take alpha equals to -1, then 2 over alpha is equal to -2. So we are going to pass through the point 2 on the x1 axis, and we are going to pass through -2 on the x2 axis. So this is 2, this is -2, and our line is going to be looking like this now. And the slope of the trajectories there would be -1. So again, some orthogonality is seen in this picture. What about the case when alpha equals to 0? So sometimes looking at these equations, some equations would be more useful for us. Okay? So when alpha is equal to 0, if I put it here, this tells me that x2 intersection is going to be at infinity, and x1 intersection is going to be at 2. Okay? But maybe, so you can actually draw this line as the vertical line here. x1 intersection is at 2, x2 intersection is at infinity. It's going to be a vertical line here. But really sometimes other equations would tell us this more directly. If alpha is equal to 0, I see that x1 is equal to 2. Okay? It's just this line in that case. The same thing is given, but sometimes some equations would tell this more directly than the others. So I have the trajectories locally horizontal on that line. And I can actually take other lines as well. Alpha equals to 2, then 2 over alpha is equal to 1. Meaning that this line is going to pass through 1 here and 2 from the x1 axis. So that is my line here. And the slope on that line is going to be 2. So we would be drawing slopes like this. So of course, you do not have to be exact here, but you need to be sufficiently exact to be able to, sufficiently accurate to be able to extract an approximate trajectory here. And finally, I can take alpha equals to -2, 2 over alpha is equal to -1, and in that case, the line would pass through here, and I would give like this. And the slopes would be -2. So an interesting thing here is that whatever line I am drawing here, the slopes that I am drawing would always be orthogonal to that line. Okay? For this system, whatever line I draw here, the slope curves that I'm drawing here, the local slopes of the trajectories, they are always orthogonal to the lines that I draw. Okay? This tells us something about the form of the trajectories actually. Okay? So whatever line I'm drawing, the trajectory slopes that I'm drawing would always be orthogonal here, like this. All right? Similarly for this one as well. This tells us something about the trajectories. Okay? And finally, let me take alpha, last finally. So I have alpha, let us say that alpha going to infinity. What does this tell us? Alpha going to infinity, this tells me that x2 intersection is at 0, x1 intersection is at 2. So you have a horizontal line, but again, sometimes when you go back to another equation, you see it more clearly. If alpha is infinity, you see that x2 should be equal to 0. So this is x1 axis, so on x1 axis, the trajectories are vertical. Okay? Like this. So you see the circles there actually. Okay? So here, using the Isocline method, if you realize that the lines that I'm drawing here would always have orthogonal slopes to them, you can see that the trajectories are going to be circles, but it is also acceptable that you draw the trajectories just like approximate circles. It really doesn't matter here. But here you see that the trajectories are looking like circles. So here, how should I choose the directions? I still didn't choose the directions. I don't know if these circles are clockwise, the system travels on these circles in clockwise direction or in counterclockwise direction. So how should I choose it? So here, just select a point here, for example. Okay, to the right of the point 2. This is the point 2 on x1 axis. To the right of point 2 on this axis. What is that point? Let us say it is 3 and let me say 0. What does the velocity vector look like according to this system? X, this is my x, then x dot is going to be x2 is 0 and x1, so x2 dot is equal to 2 minus x1, which is minus 1. Okay? So you see that here, this is my velocity vector for this point. So in which direction do I have to take the circles here? Clockwise or counterclockwise direction? So we see that this velocity vector is pointing in that direction. Okay? Meaning that I need to turn clockwise here on these circles. Okay? You can see it from the first equation as well without doing anything. If x2 is positive, x1 should increase. If x2 is positive, meaning that we are considering the first and the second quadrants here, if x2 is positive, x1 should always increase. So you see that above x1 axis, the trajectories, the x1 coordinates are always increasing on these trajectories. And similarly, if x2 is negative, x1 is always decreasing on these trajectories. That is how you can select the direction as well, by using either of the equations. So this was the application of the first method. And here, maybe it is not clear to you why I draw circles there. I draw circles because on each line, the slopes of the trajectories, the slopes that I have drawn, the slope lines that I have drawn were orthogonal to the lines I have drawn there. So these lines were always orthogonal. That is why I draw circles there. But here, it is an easier way to see that this system is also going to give circles as their trajectories. And it's going to be using the first method that we have seen. So if I write dx1 over dx2, that is actually It doesn't matter which one you take here, but in the Isocline method, I use dx2 over dx1, so why not use that one? As I told you, it doesn't matter. I have this, okay? dx2 over dx1 is given by this, and our first methodology tells us that I need to collect the like variables on each side. So this is x2 dx2 is equal to 2 minus x1 dx1. And then integrate, okay? x2 square over 2 is equal to 2 minus x1 square minus over 2 plus c. Now take this to the other side. 2 minus x1 square over 2 plus x2 square over 2 is equal to c. Multiply both sides by 2, and this is square here, so I can write this as x1 minus 2. It doesn't matter. x1 minus 2 square plus x2 square is equal to 2 times c, but 2 times c, let us say that it's again c. It's again a constant. So you see that from the first method that we have seen, you can obtain the equations of the trajectories of this system. And what does this tell us? This is an equation for a circle with the center point 2, 0 here, okay? And the radius depends on the initial condition. Radius is constant, and it depends on the initial condition that you select. Okay? So that is the application of the first method into our system here. So you see that it is useful in this part of the course to know actually equations of such simple curves. And here, again, this differential equation that we obtain is separable, as you see here. So I have so that I can actually separate x1, x2 variables and x1 variables on each side of the differential equation. Otherwise, method 1 would be useless. Similarly, in the isocline method, after you select your alpha, if you equate this to alpha, you need to be able to draw the curves that would result from that equation. Okay? And in this case, those equations gave us some lines which were easy to draw. Similarly, in order to be able to apply the isocline method, those curves should be easy to draw. So if the system is much more complicated than these type of systems, if these equations turn out to be complicated equations, or if this differential equation turns out to be not solvable using the separation of variables, then of course these methods cannot be applied. In that case, actually it is most of the time that we need to use a computer in order to be able to draw phase plane trajectories. So that completes this first lecture of this week in EE404. In the next lecture, we're going to solve an example, and if time permits, we're going to start a new topic that is called limit cycles. That's all for this lecture. Thank you for watching.